Okay, in physics, work is essentially manual or mechanical work. So let's take a look at this. We've got a block here and we want to move it. So to move it, we have to do work onto it. So we apply a force to move this block a distance d. Okay, so to move this block, we must do work on it. Hence, we have to transfer energy to it. So for example, if this person was pulling the block, they would have to transfer their chemical energy to kinetic energy of the block moving. Okay, so the work done or energy transferred for moving this block would be the force times the distance moved. So for example, if this block here required a force of 10 newtons to move a distance of 2 meters, the amount of work done or energy transferred will be 20 joules. So 20 joules of chemical energy by the individual would be transferred to the block to move it. Now if the block is moving, the block has kinetic energy. Okay? So if we now consider moving a block upwards, so this block is attached by a rope to a pulley system. Okay, so if I was to apply a force here and move the block up a height h, okay, so the work done by the pulley, so to speak, would be, again, work is force times distance. So let's say, for example, the force required to move this block is 100 newtons. Therefore, the work done to move the block will be 100 times, and the distance here was 3 meters. 100 times 3, so it's 300 meters. Okay, now what we can do, we can take a step further. Let's consider still work is force times distance. Let's remove this 100 newtons. And let's say, for example, the mass of the block is now 50 kilograms. So therefore its weight, okay, will be 50 times gravity. So in this case, if we take gravity to be 10, just to make the maths easier, is 500 newtons. That's the weight of the block. So therefore, to lift the block up at a steady speed, the pulley would have to provide a force of 500 newtons. Okay, so again, the work done would be energy transferred, which is 500 times 3. So it would be 1500 joules. Now, at this point, the block would move up to here. Okay, now at this point, at the top of the pulley system, the block would, for example, be here, and at this point it has gained gravitational potential energy. Right? Now, since we looked at work done is energy transferred and force times distance, let's look a little bit more on kinetic energy. Okay? So kinetic energy and gravitational potential energy. Okay? So the equation for kinetic energy is half mass times velocity squared, or it can be written as mass velocity squared over 2. Remember, we're only squaring the velocity here, okay? We're not squaring the whole thing. Students always have difficulty with this. Now, gravitational potential energy can be written by mass times gravity times height. So basically all this means is that kinetic energy is determined by the speed of the object and potential energy is determined by the height of the object. And the questions we normally get is work done in either increasing kinetic energy if you're speeding up an object or increasing potential energy if you're lifting up an object. We've got to get that clear first of all. Right, now we're going to combine work done with kinetic energy. Alright, so let's say, for example, we have this car here, my amazing looking car, right, and the engine if you consider, provides the force here. This is the driving force of the engine. Let's not worry about friction at the moment. Alright, we'll come on to friction later. So, if I provide, say for example, say 1,000 joules, right, of the work done by the car, alright, and driving force is, say for example, 100 newtons, alright, so now we can actually work out the distance traveled by the car. Alright, so if you go for force, sorry, my mistake, let's take it back a second. Work is force times distance. Rearranging this, distance is work over force, so it's 1,000 over 100, which is 10 meters. So that car will move 10 meters. Now, if we assume all the work done here is transferred to kinetic energy, right? All the work done is transferred to kinetic energy of the car, right? So now we know that the work done is equal to the kinetic energy of the car. Therefore, 1,000 joules is equal to half mv squared. Now let's assume a really small car. We've got 100 kilogram car. Okay, really tiny little car. Alright, now we can rearrange this equation to find out what the speed of the car would be. Alright, so all we need to do is V equals 2 times 1,000 divided by 100 kilograms, square root the whole thing, which will give you an answer of 4.4 meters per second. Okay, in this example we'll look at work done and gravitational potential energy. So let's assume we have this mass here and a pulley doing the work here, and essentially the wire is here and it's going to lift upwards to a distance of 2 meters. Now let's work this out. Imagine all the work done by the pulley is going to lift the block, and so the block is going to gain potential energy. So let's work out the gain in potential energy of the block. So potential energy is mass times gravity times height. Now let's say gravity for 10 to be example, to make it easy. 5 times 10 times 2. Okay, so we have 1,000 joules. Alright, so if you ignore friction, we know all the potential energy is being transferred to work done. So let's look at this. So mgh is equal to work done, or mgh is equal to force times distance. We can now actually work out the force required to move that block. So we know that mgh is 1,000 joules, so 1,000 equals force times distance. So therefore force is equal to 1,000 divided by 2, which is 2 meters, so it's 500 newtons. So therefore 500 newtons of force is required to move that block. Okay, let's now consider work done, potential energy, and actually considering friction. So let's think about this. We have got our block here. I'm going to slide this up to the top of the ramp. We're going to have a pulley again here doing all the work, lifting up the block. At the top of the height, it would have gained 2 meters in height. The mass of the block is 2 kilograms, and the distance from the top to the bottom to the top is 5 meters. So let's recap. All the work done by the pulley here will be transferred to potential energy, plus because we're including friction, some of the energy will be lost due to friction, because we all know that friction wastes energy, and it wastes energy in the form of heat. So let's consider now, first of all, the actual potential energy at the top of the slope. So mgh, that's potential energy. We know the mass, which is 2. Let's take gravity for 10, just to make it easy. Multiply by the height in 2. So that'll give us 40 joules. So 40 joules of energy when the block is at the height, or at the top of the block. Now, let's imagine the actual work done is 100 joules. So, because we're taking into account friction, work done is equal to gravitational potential energy plus lost energy due to friction. Now, we can work out the lost energy. So the lost energy is, in this case, will be 100 minus 40, which is 60. Now, we know that the energy lost to friction is 60, right? Reason being, we have, or I have told you, the work done is 100 joules. We could work this out, but I just told you this to begin with. So therefore, the work done, 60 joules, is lost by friction. We can actually work out the force of friction. So again, the force of friction in this case will be energy lost or energy transfer, so it's still work. It's force times distance. So 60 joules is the energy transferred or lost due to friction, equals F, and the friction occurs over a distance of 5 meters. Alright? So times 5. Rearrange this, is 60 over 5, which is 12 newtons. So therefore 12 newtons of friction force is produced or generated when moving the block up the ramp. Just remember, in this case, the lost energy is the energy lost due to friction or work done against friction. Remember, it's the work done against friction, and hence, once we know that at 60, we can apply this equation to it and work out the force of friction. This is a very tricky concept. Okay, now let's consider a car moving with kinetic energy, obviously, and relating work done and energy lost due to friction. Right, so we have a car here, obviously, my brilliant car, mass of 100 kilograms, traveling at a velocity or speed of 3 meters per second. We have a distance here, the braking distance here, and a braking force of 90 newtons. Right, we can work out its kinetic energy. So kinetic energy is half mv squared. So in this case will be a half times 100 times 3 squared, which will then give you a value of 450 joules. So this car is traveling at has got kinetic energy of 450 joules. Now, when the brakes are applied, we've got a braking force of 90 newtons. So what we're going to do is transfer this kinetic energy into friction energy to stop the car. Right? So the kinetic energy goes into work done against friction, or work done with friction in this case, because we're braking the car. So kinetic energy is 450 joules, which equals force, the force of friction by the brakes in this case, let's ignore the tire friction at the moment, times the distance. So we want to find out what is the braking distance here for a car traveling at this speed of this mass. Right, so 450 joules, the braking force we know is 90, so 450 is 90 times d. The distance is 450 over 90, which is 5 meters. So this car here will take 5 meters to come to rest. Alright, and this way we can work out the stopping distance of a car at particular speeds if we take an average mass and braking distance. So this is again relating kinetic energy to work done against friction.